Okay, so hands to yourself, Sam. On YouTube. Okay, so we're doing lesson number 4, so we got to skip lesson number 3, which is a nice treat for us. So today is about absolute value transformations. And part of this lesson will actually feel like a review of lesson 1 way back. But that was almost a week ago, so it's probably a good thing we're going over this again. Okay, so if we go down to this, we're going to start by graphing. So in your y1, I just want x minus 1. And then in y2, I want the absolute value of x minus 1. Okay? And maybe make one of them a big fat line so that we can see the difference between the two. Or that. And so if you can't remember how to find the absolute value, you go to math, over 1, and then 1, x minus 1. And like I said, I'm going to make it a big fat line. Okay, and then you hit graph. So you get something that looks like that. Okay. So yeah, that's not easy to see. There we go. Like that. Because I wanted to have a dotted line. Okay, so we should get something that looks like that, right? And so we know that this one here is our x minus 1, and this one is our absolute value of x minus 1. So if you remember all the way back to last Wednesday, we said that the negative part of the graph, so this part here, is the only part of the graph that actually changes, right? The positive part of our original graph stays the exact same, but the negative part is reflected in the x-axis. Okay? So if you look at this stuff here, this is good notes for us. So we'll say, when the function is greater than 0, so when it's positive, right here, the graph of the absolute function is, Andrew, for the positive part here. Yeah, so the absolute value stays the same, right? Same or identical. Okay, so for this portion of the graph, we'll even highlight it. Stays the same. Okay? When the function is less than 0, so the negative function, which is this part I've circled right here, the graph of the absolute value is the reflection. Okay? So it's a reflection in the x-axis. So if you think back all the way to our quadratics unit, how do we show a reflection in the x-axis with our equations? Awesome. A negative, right? So that's why all of our negative values become positive, because it's like taking the negative of negative, right? So if we go down to this one, this time in our calculators, I want y1 is equal to x squared minus 4, and y2 is equal to the absolute value of that. Okay. You got it. Yep, if there's an x squared, it's a quadratic. Okay. So this time, I'm not going to try and draw it. There we go. So Here you can see that the same thing is true. Where the graph is positive, so here and here, the two graphs are the exact same. But where the graph was negative, it becomes reflected, like that. So even when we're working with quadratics, it's true. So it's the same rules for linear as there is for quadratics this time. So we say, yes, our observations do apply in this example. And we can say the function is less than 0. The graph for the absolute value is reflected. Okay. And you can even write here in brackets like negative to positive. Okay. So where it's positive in the original, it stays positive. Where it's negative in the original, it becomes positive. Always. Okay. Basically, they're just showing you that it's always a reflection. Okay? So I want you guys to think of it as a reflection, because if you just always think like, oh, I always just go negative to positive and I do this, like, the reason we have these rules is because it's a reflection. And I find if you don't know why you have a rule, you're more likely to forget it. So think of it as a reflection. So this stuff here is quality study sheet material. Okay? And basically all it's saying is that when the function is greater than 0, so when the graph is in the positive side, so above the x-axis, the graph of the absolute value is identical. So where it's positive, it's going to be the exact same in the absolute value. Okay? Just like when we were looking at absolute value numbers, we know that the absolute value of 2 is 2, right? Okay? And then it says where the function is less than 0, so where the graph is below the x-axis, the graph of the absolute value is a reflection. Okay? So it's basically just saying that the only place where it changes is when f of x is less than 0. Okay? So for here, they say this is the original graph. So they say the graph of y is equal to the function is shown, and they want us to sketch the graph of the absolute value. So we know that when something is positive in the original, it stays the same in the absolute value. So that will stay the same like that. Okay. But then all of our negatives get reflected. So say we say this point is like negative, I don't know, -4 and -2. Just our y gets reflected. So it would be like -4, +2. Okay, so our new graph would look like that. Okay, so for this one, because this is our original, this one's kind of different because everything is negative, right? So nothing will stay the same in this graph. But one thing we know is that, okay, our y-intercept is at -1 here. So when we reflect it in the x-axis, our y-intercept will be found at +1. Okay? Just like that. Yeah. Okay, so, okay, focus. So we know that our y-intercept changes when it's negative. So when it's positive, like right here, it doesn't change. But if it was negative, it would be reflected. And one nice thing about these is that our x-intercepts never change during a reflection, right? So here our x-intercept is still -3. Here on this one, we still have no x-intercepts. So that's one nice thing, is that we know that those will stay the same. Okay? 4. Some notes. Okay, so in case you can't remember, we know that domain is all the x's, and the range is all the y's. Okay? So when we do a reflection, does the domain change at all? Exactly. So if we look at this graph here, this one, we can see that our values for x don't actually change. They still go in the same places as they would have here. Even in this one, when we look at our reflection, we reflect from a -4 in the x, and it stays as a -4. So we write that the domain stays the same. Okay. So what about the range, our y values? There's a different R word. You got it, reflection. Yeah. Okay, so they say that. Okay, so this is good notes for you, Sam. So they say the range of the absolute value function oh, sorry, that's an of. The range of the absolute value function and our original are the same when the original is positive. So we'll say y is equal to f of x is greater than 0. And we say, and all negative f at x, so that's our reflection, right? Just like in our quadratics unit, we showed reflections by putting a negative. We do the same thing here. When just pretty much our equation, right? So they're saying so the range of the absolute value and the original are the same when it's positive, and it's the same as the negative function, or the reflection when our function is negative. Okay? And so for our x-intercepts, what should we write in our notes about that? Absolutely, they stay the same. And then our y-intercepts. What do we know about our y-intercepts? Always? What about this instance? No. So we need to come up with a general. Something that's a rule that always works. Pardon? Yeah, so our y-intercepts will always be positive in the absolute value. So that's a good way to put it. We can say when it's positive, it stays the same, and when it's negative, it becomes positive by reflection. Okay? So we say if the y-intercept of the function is positive, the y-intercept stays the same. Okay? And then if you want in brackets, you can even write like positive to positive. Okay? And then we also need to know for our notes what happens when it's negative. So if the y-intercept of the function is negative, the y-intercept is reflected. Okay, so we can even put in brackets opposite or negative to positive. It is. Okay, so that's all there is to this lesson, which is nice for us. So the homework is 1 to 7. Okay, so the homework is 1 to 7. The homework isn't too long. I expect everyone will be able to finish in class. But some of it is kind of tricky. So if you have a question, let me know.